Alright everybody, so we are meeting here today to discuss the inclined plane experiment. Though this particular experiment cannot be performed in the form of an internal assessment, this could certainly give us a very good idea as to how we can process the data that has been collected. So let me give you a brief overview of what this experiment is all about. If I need to frame a research question for this particular experiment, it would be somewhat like this. How does a change in the angle of inclination influence the overall mass suspended from a pulley to balance out a frictionless trolley on the inclined plane? So that would be a probable research question. How would the experimental setup for this look like? So I'm talking about the presence of an inclined plane. Let us go in with an assumption that this angle here is theta, the angle of inclination. I'm talking about the presence of a frictionless trolley. So let us consider this as a frictionless trolley. Alright, there you go. I'm also talking about the presence of a pulley system here. Now, since it is frictionless, it's quite obvious that with this angle of inclination, the object would in fact roll down. To avoid that from happening, we would be having a string attached. This is a pulley system. We have a mass being suspended from there. Say, consider this as capital M. I have the trolley of mass lowercase m. So if I draw the free body diagram for the trolley here, I would be having an mg in the downward direction and a normal reaction over there, which is always perpendicular to the surface on which the body is present. If I resolve now mg into its components, and you might ask, why should I resolve mg into its components? Because we pretty well know that all those forces are resolved which are neither perpendicular nor parallel to the surface on which the body is present. It's quite obvious that mg is the force which is neither parallel nor perpendicular to the surface on which the body is present. So when I resolve this mg into its components, I would have one which is perpendicular to the surface and the other which is parallel to the surface. Simple math would give us that this particular angle here would be theta, the same as the angle of inclination. Therefore, this component, which is a perpendicular, would become mg cos theta, and the one which is a parallel to the surface would be mg sin theta. So I'm considering to ensure that this particular trolley is balanced or is in equilibrium position so that it does not move up or down, it continues to remain at rest. Alright, so in such a scenario, based on this particular free body diagram, here I forgot to mention the tension in the string. Alright, now based on this free body diagram, am I allowed to write capital N, that is the normal reaction, is equal to mg cos theta. These two forces would balance out with one another, and to balance out mg sin theta, I would be having the tension in the string. Right. Now at the same time, if I consider the mass that is being suspended, the two forces acting on that particular body, they would be capital M into G, that is the gravitational force, and the tension acting in the upward direction in the string. So from the free body diagram for capital M, I can certainly write that the tension is equal to capital M into G. Since this is one continuous string, it's quite obvious that the tension in the string here and the tension in the string here would be the same, which then goes on to say that capital M into G is equal to mg sine theta. Needless to mention, the G here and the G there would strike off with one another. I would end up having capital M is equal to m sine theta. Now this is in the form of y is equal to mx plus c. So if we carefully consider, plotting a graph with sine theta along the x-axis and the mass that is being suspended along the y-axis should yield us a line passing through the origin, and the gradient of the line here, the gradient should give us the mass of the trolley. So this is a very simple experiment, can be conducted, and we could always verify the experimental gradient versus the theoretical gradient by measuring the mass of the trolley on a digital balance. Compare the two of them to determine the error in the entire experiment. Let's check how that can be done in the next video.